Céline Acary-Robert. I'm a scientific computing research engineer in Grenoble Alpes University. I work at Applied Mathematics at GRICAD lab and also on the computing Meso Center GRICAD. So I'm part of the French reproducible research network, and I would like to thank the organizer to invite me for inviting me to talk about open science in general and reproducibility in scientific computing in particular. So I'm going to make a short introduction around the concept of open science, reproducibility, and the difference between the two. Then I'm going to deep in detail with open science, context, and a short how-to. FAIR principle I've been already talking about. Then I will introduce the concept of reproducibility, detailing historical context, international context, and hint on terminology. That is an important point. Finally, I will focus on computational reproducibility. That is the aim of this school. I will give you some issue examples and some good practices. So if we start from the UNESCO definition of open science, it's a large movement to make scientific research transparent and accessible. The key point is to all levels of society. This is embedded in a larger framework that includes all others components on the general society. So it concerns publication, data, physical samples, and of course software. So what it means in research, each element of the research process should be publicly available, easy to find and to use. Projects hidden behind passwords or technical difficulties are not really publicly available. They are difficult to use. It should be transparent with appropriate metadata to explain what are these, where how these research outputs were produced and what it contains, and reusable. In particular, they need to be to have a license. So, what benefits will the research bring? We have seen that in the precedent talk. It increases the speed of knowledge dissemination, accelerate scientific progress, and there is societal and economic benefits, support innovation, education, and an important point also, society and general public confidence. Let's have a look at the reproducibility meaning, the main concept. You have a publication, two teams. We suppose that the data and code are open on a public archive, and the two teams want to reproduce the result present in the publication. This is the first step for our reproducible results. They want to reproduce the result for eventually change the parameter value, extend some functionality of the software. Of course, we need the code, the associated data set, the article on Open Archive. So open science principle is a really necessary step to ensure reproducibility. So what is the interest for you? You have a suggestion from a reader, a colleague to improve something. You want to reuse your own code 2 years later. And a PhD student on your lab want to compare his or her results with a former study. So if the results in the article are reproducible easily, you can quickly reuse your code. At each stage of the development process of your software, you can reuse your code and trust the specific version, and you save a lot of time. For the research, it makes the results sustainable. That is a key point of reproducibility. You build trust with reader or reviewer, the reviewers of your paper. If they are able to reproduce the result presented in the paper, they trust your results. It increases research efficiency by reusing existing work and improve regarding software or code, its quality, bugs can be reported. So finally, it increases confidence in results in research results. Now I will focus on open science. So we have seen that the objectives are various. We have detailed all of that points. Just some key dates. Started in 2002 with the Budapest Open Access Initiative. It's the foundation of the open access movement. It's not so quite recent, finally, near 20 years that started in Europe. In 2003, the Berlin Declaration was the cornerstone of open science in Europe. In 2016, the launch of the EOSC, so I won't detail this project. And finally, from 2021, the Horizon Europe program. It's the fundamental point is that open science become a core principle of the EU research policy. At the international framework, I just put on the slide a few initiatives. The Center for Open Science in the USA that provide infrastructure through OASAFE for training and meta-research. Some European programs to promote open science, such as Open Air, so EOSC, and more recently, a global research initiative on open science that aims to analyze the impact of open science policies in research and increase their efficiency and the strategies. So just a hint for open science in France, there are some laws for open science and integrity. For French people, they're called the Loi pour une République numérique. There is a central organization called the COSO, Committee for Open Science. It's led by the French Ministry of Research. And more locally, in each university, you can find some units, local data management units called Atelier de la Donnée. There are some people in charge of helping researchers to open their data. In some of them, they deal also with code and software, but not in all units. So the main objectives are to generalize open access to publication, structure, share, and open data from public research, that is to say promote fair data, promote also open source code software from public research, it's the key point for this slide, and transform research practice to make open science the standard. So it's a long way, but there is some progress. I won't detail the fair definition, but just add a point. You have to, from public research, public funding, you have to open your data, but some restrictions are taken in consideration. It can be as open as possible and as closed as necessary. If you work on a defense army field, you are in contract with private company, you can share only metadata and not the data. There are two references. One, an article in Nature, and a part of Skills for EOSC called Fair by Design. It's a methodological guide, very good design to help you to make your data fair. Regarding the code, we can follow the same guideline. I won't detail the point, but there is another initiative named Code for Open, Document, Execute, and Collaborate. The objective is to same a quite different thing just for code. So I put the reference on all. I think it has been published, but I'm not sure. So in a summary, the data sets have to be available on a repository with a persistent or perennial identifier, such as DOI, some metadata, complete or not, license, and the documentation. The same for the code, available on a public forge with a persistent identifier, license, and documentation. Finally, the article in an open repository such as or archive. So just a little remark, repository with institutional endorsement are better to ensure reliability and sustainability. We have seen that some private repo being closed recently. I put a link on a passport for open science. It's a short guide for PhD students to explain how you can open your work. It's from the COSO website. Of course, there are some barriers, and there is a short list here. A lack of training and awareness. It's true that it takes time, required effort, and this time and extra effort are not enough considered for career, for example, or for promotion. Some publishers expect some openness, but in the CV it's difficult to promote it. And two last points, the fear of being judged by other researchers and fear of the work being reused before publication, but you can set an embargo if you need. So benefit, we have described it largely. I just want to cite two articles that said that open science practices increase citation. So the first one, it's from 2016, but there is a more recent one in 2025, and that explained that the open science products are more cited. The last point is that open science, it's really a pillar for reproducibility. Without open science, you can't hope to reproduce results in article. I put this picture. It's an extract of a book called The Turing Way. It dated from the Alan Turing Institute. It's the UK Institute for Data Science and AI. This book is a very complete book on open science techniques, technical details on open science and reproducibility also. And there is a lot of picture in this book from Scriberia. So you can see that it's a way to go to open research. At first, you fear to share your data and your code, and at the end, you benefit from the work of other people. You increase your network and your work. Let's have a look at the reproducibility context. So why reproducibility matters? There is in epistemology a fundamental principle that scientific results have to be tested and validated by other people and researchers to really become a knowledge. Each result needs a consensus to become a knowledge, and the reproducibility ensures that the validation by other people. Sorry. Moreover, it ensures reliability. It's helps to verify that conclusions are not due to some errors. It optimizes resource use, better use of time, funding, infrastructure. It avoids unnecessary duplication of experiments. You can reuse a work already published. And of course, it encourages rigorous and transparent practices. If you provide reproducible research, that means that you have used rigorous and transparent practices. So there is various studies about the reproducibility of results. Researchers started to study that reproducibility in published results in the 2000s. These studies are part of a research on research methods called meta-science or meta-research. Maybe you have heard of this word. It's an interdisciplinary field that aims to analyze, evaluate the research methods in general. So a lack of reproducibility in many publications was identified in the early 2010s and called reproducibility crisis, as my colleague told you. From this study of Baker in 2016, this survey, the main factors that appeared was first the data or code were not available or not usable, but there are also some other reasons: selective reporting, publication rates, lack of time, lack of awareness, of course, human errors in publication. You can put a wrong parameter, for example, but in some rare cases, fraud, and it's far from being the most important factor. I present here 3 special studies. The point that I not talk about is that all scientific fields are concerned with this crisis. There is no good researcher and not endless or good researcher. So in economy, there is a study published in 2017. It was conducted over 60 articles with available data and code and pre-analysis. And only 1/3 of the articles were reproduced and 10% after contact with the author to get some more information. The same in applied psychology. This study was conducted between 2015 and 2018 in the review Cognition. There were 35 articles with available data. At the first attempt, only 11 results in the article were reproducible. More recently, there was a 10 years reproducibility challenge that have been launched in 2019. The main objective was to rerun a published code, your own published code, 10 years later. So the main difficulty that appeared was to find the code and set up the same software environment. We will detail this aspect later. One researcher involved in this challenge had its own code on a floppy disk. So it was hard to use it. At the international level, taking into account these studies, there is an emergence of structuration. It's a matter of concern, as I said before, in various scientific communities. And some reproducibility networks have emerged in Europe, mainly, but there is one in Canada, one in Brazil, and one in Australia. The African continent is dashed because it's one network for all the continent. That it's a real work to make researchers from all those countries working together, but they succeeding, they realize training and something like that. So it's very interesting work. So each network has its own structure, and so the founding are different, the local organizations are different, and so on. Global federation is rising. Called the GFRN. The link is clickable. You can have a look at that. It's very recent, and it's in charge of organizing activities, pool efforts to raise awareness of the issue of reproducibility, and also foster best practices exchange at the international level, best practices, conference and workshop, and training materials. From the European point of view, there is some European project in the call Horizon Europe that deals with reproducibility. We can cite Osiris. In France, the INSERM is widely included in that project and is very active in the field of reproducibility. Present now the French network that I'm involved in. It was created in 2023. It's an informal structure with only people that the member have subscribed to the mailing list. So I put the QR code. If you want to join us, you are welcome. There is a strong support of the French ministry with a project manager dedicated to the network. And we have various activities, webinar to share good practices. We try to cover many scientific fields. We organize workshops. we set up a bibliographic database in a Zotero organization. And we have a special working group around software to write the best practice card with how to manage your software. But there is some technical hints and some link with tutorials for all tools that are cited in the code. So I put the URL of the website, and so you can subscribe if you want. Until this slide, I have talked about reproducibility, but there is a great diversity. The good practices to ensure reproducibility of the results will depend on scientific discipline, implemented techniques, data management, and so on. So there is a strong need to fix the terminology at an international level. There are different kinds of reproducibility. We call the empirical reproducibility concerning the experimental science. If you want to ensure the empirical reproducibility, this is the record of the condition under which the experiment took place. The observational one, if you you have to record the condition under which the observations were made. Statistical one, it's the evidence of the reason why a result is statistically significant. And finally, computational one, it's the record of the production of a result on a computer. I will deep in detail on this notion. So, for example, if you work in chemistry, in the publication you will share the parameters of the experiment, for example, temperature, pH, and so on, the element of the experiment, the chemical product, for example, and the protocol. For the observational one, you have to share the observation protocol, context, duration. These lists are some examples, they are not exhaustive, of course. The step of observation, and so on. You have to share each parameter that is needed to recreate the result, the published result. So this, the conditions in the case of experimental or observational science are sometimes very hard to recreate. For the statistical one, you will share the justification of the choice of the statistical test, the choice of the model parameters, for example, threshold value, sample size. If we deals with artificial intelligence, you have to share the parameter of your model, the dataset that have been used for the test, the train, and so on. So the list can be quite long. And for the computational point of view, you have to share your code, your version, the workflow, how to use your code, the parameters file, of course, but also, and we will deep in detail later, hardware, software environment, dependencies, datasets, and so on. We have to notice that nowadays computational aspects are very transdisciplinary. Even in humanities, people deal with statistical analysis of their data through Python program or Python notebook. And so it's a matter of concern in a lot of scientific fields. Sometimes in some documents you will heard about repeatability, reproducibility, replicability. So the definition depends on the scientific fields. For the moment, there is no standardization. We have seen that the reproducibility of a result is to reobtain the same result, but the notion of same result depends on the scientific field that you are working on. It may be the same conclusion, equivalent result. So in each specific scientific field, have to define what is the same result, in fact. I'll present this picture. It's extracted from a blog of Konrad Hinsen that is deeply involved in reproducibility in scientific computing. I've put the link. I show you the different stage of the execution of your code. At the first stage, you have your own code until the hardware in which your code is running. So at the first stage, you have your script, your notebooks, your workflow. This is your project-specific code. It will use some domain-specific tools, some domain-specific libraries, such as for the example he took, it's in biomolecular simulation, GROMACS, MMTK, for example. These libraries use themselves some scientific infrastructure, such as BLAS, SciPy, or any Python package that you need, some library for data format, for example, HDF5. This use the next stage, the non-scientific infrastructure that's called compiler, interpreter, such as GCC, Python, and so on. All this is running on an operating system, Linux, or Microsoft, or WASL, and on hardware, a processor type. So you have to be conscious that at each level, at each stage of this picture, tools has their own version, and you have to control it. So from the developer point of view, the code looks like a main routine, some subroutine, some few library, but in fact it's a pile of noodle. It looks like the picture on the right if you consider all the dependencies of each element that are on the previous picture. And it's a simple one. For example, if you have a look at the version of Python 3, before, well, it's quite old version of Python, but I think we can find some example, more recent example. Between Python 3.5 and 3.6, the default value of relative tolerance and absolute tolerance have been modified. So the result of the function isClose from a quite current package called math was false before 3.5, 3.6, and true before after. You can see that the behavior of your program can drastically change, changing the version of Python. It is the same thing. Well, I cite two examples on Python interpreter and packages because it's a very fast changing ecosystem. So you have to be aware of that using Python. In NumPy, between at the stage of the version 2.0, they wrote a migration guide because there were a lot of changing in the syntax of function and so on. The same in Panda, for example. So you have to be aware of this change over time. The second example, it's an example of compilation and parallelization that lead to different results. I consider this series a simple series depending on the n parameter. So I used a very naive algorithm with a double precision and OpenMP parallelization pragma. It's a Fortran program, a quite recent G-Fortran compiler with the option OpenMP. And if we run it for quite small value of the parameter n, over 1 million, we can see that sequential and parallelized OpenMP one thread give the same result. With 4 threads, it leads to same result. But if you use an optimization option, results begin to change and up to the 6th digit. So maybe your conclusion does not depend on this digit, but maybe yes. It's if we increase the value of the parameter n, the problem appears more directly with the 4th thread parallelization. And executing the same program on a CPU, one on a GPU NVIDIA V100 with OpenACC pragma lead to the same difference between leading for a large value of the parameter n. So you have to decide what level of numerical precision is significant for you, and share your optimization option and the way you run your result. So good practices are to deal with interpreter version and dependencies. You have to share your software environment, precise what the version had been used in your study, and maintain the code over time. Regarding the precision, you have to choose the significant precision you need and share compilation and execution details. If we have a look at the good practices regarding the software development, we will learn this week a lot of tools that will be very useful. So to improve portability and reusability, you have to implement best practices for development. Use a reproducibility-oriented software manager, such as Geeks, Nix, Pixies, which is a Conda base and that we will use this week. Think carefully about a license before writing your code, because this will regulate the use of your code, and it could be an important point for the future of your development. Use a versioning tool such as Git and a software forge to automate test and documentation, and write this documentation. Regarding software dissemination, even before publication, the repo should contain, of course, your code, but also author and contributors, a license file, a description of the code in a README file, the workflow how to use it, and if you want external contributors, you have to write a guide how to contribute. Regarding the execution stage, the repo should contain the description of the hardware, the precise description of your software environment, and the way to recreate it easily. Input parameters file and workflow for execution. Also, there are a lot of useful tools to do that. Finally, writing your publication, you have to cite your software. And the best way to do that is to use the software heritage tools. So I don't know if you know these tools. No. Okay. Software heritage is a foundation that have to preserve software in the source code form. They collect every open public project on Public Forge, and they archive them on a repo, on their own repo. I can't remember exactly, but last year there were 800 of tera of code archive in some place. So they curate, make accessible the collected software, and preserve it in very long term. So what is interesting for you, it's that software heritage provide a persistent identifier for your code in a Public Forge, but also for each part of your code. So you are able to identify in time each part of your code, and this is through the SWID, an identifier called SWID, that you can put on your publication. So the reviewer has the access to your code through software heritage and the URL of your forge. If all steps before have been respected, every detail is in the forge, and you provide only the SWID on the publication. So in the article, you have to share the datasets with Duo OI, share the code with the SWID, and put your article on Open Archive. So as a conclusion, there is a lot of things to do, but the key point is to slowly change your habits, gradually adopt good practices, think about your own practice and what can be changed at first easily and learn tools to do that. So at the beginning, it requires time. It's for sure a gradual process, but you will save a lot of time later. You win rigor, time, confidence. The reviewer also save time and get confidence in your work. You can share your code with your colleague. And finally, public in general, there is a confidence in science in general also. I put here some bibliographical references. 2 MOOC from the FunMOOC platform on reproducible methodological principle. They are easy to do. It takes time, but for PhD students, or at least in France, you can validate that to your doctoral school. So there is a lot of examples. It deals with data and software, and it's very interesting. And there is some other references. So thank you, and enjoy it. So just in for the question, we cannot say that reproducibility is improving or not, because there is no exhaustive study on even one scientific field to say that it's improved or not since 2016, in fact. So I'm afraid the answer is not, but it's only my opinion.
Questions?
Repeat this last statement. You don't believe that it has changed in the last 7 years, or what was your statement, your last one? I didn't get it.
Oh, I can't say that it's the reproducibility improve or not, in fact. I think nobody can say if it's improving or not, because there is no exhaustive studies. If that was that point that you asked?
As it was just because I couldn't understand you acoustically. I have another question. You mentioned this Plan S from 2018, and at this time all people were a little bit nervous what it means. What is the situation now after 7 years? Because the main publisher like Nature and so, they never joined this deal. Will they come in the foreseeable future into this, or it's...
No, regarding Open Science, I can't answer I'm not able to...
May I ask, perhaps,
yeah. In France, it's mandatory, but at the European level, I can't. I'm not able to answer.
Since the publication of the FAIR principles, that is not open science, but a part of open science, that means that for open science, you need to apply FAIR principles, at least, but you need also other components. For FAIR principles, they are now in an European circular since 2018, so 2 years after the FAIR principles. But after, in several countries, they didn't apply that in their own law. So the difference between countries in Europe makes that not well applied everywhere. It takes time to be explained to everybody. And as we have seen at the beginning, when I've said to everybody, can you raise your hand if you know well FAIR principles? Not a lot of people have raised it. So we have a work to disseminate and to increase the skillness of people in each community.
What's the situation in France? Do you have it implemented as well?
In France, now, just since 2 years, approximately, it is working a lot in Atelier de la Donnée in each university. But indeed, it is an ongoing process. For instance, the main target in France are PhD students and young people in postdoc and things like that. But it takes time to disseminate to all the layers of research activity. And for most of the communities, they are not aware, or they are not skilled, or they don't prioritize that at the good level today. For instance, the semantic part is really complex. It needs to organize peoples in communities, and that's not the fact for lots of communities. But indeed, we need to increase that, and that's the reason why we are here today.
It's mandatory from the law, but in practice, it's not the case everywhere.
I was going to comment about CTO, but maybe you wanted to say?
No, I wanted to make a more general comment that there unfortunately also has been some pushback to the open science because mainly of a real or perceived competition with Chinese experiments. So China is building a lot of experiments. You have the FAST telescope, which is a 500-meter radio telescope, similar to the now defunct Arecibo telescope. You have LASSO, which is a gamma ray instrument, which extends very similarly to what CTA has planned. You have 2, I think, proposals for ice cube-like detectors or KM3-net-like detectors in the South China Sea. And in our collaborations, we are from management, we're getting pushback to being as open as we want to be, with hints that this will help our Chinese competitors, right? So that it's not as easy. We are not making unimpeded progress, let's say, by educating more people. There's also higher up political discussions in both directions. France and other countries requiring more open science, better reproducibility, but also from the political standpoint that we gave you all of this money, please do something with it and not let the Chinese competitors overrun you.
Thank you. I wanted to ask something you said at the beginning for the motivation, and then you repeated in the conclusion. You said that for the general public, open science is good because it encourages confidence in science. But is there really an evidence for this? I mean, are there any studies, anything that we can properly say that the general public trusts science because we're open?
I think for open science, yes. For reproducibility, no.
Okay.
But I can't give you a reference now. But I think there are some sociological study about that.
Okay.
I can say something more. Just, as you know, I'm working in a specific area in BSL4 laboratories, biosafety level 4. It's not open science, and people don't trust it.
It's the reverse.
But would they if that was open? Other questions? I had one about at the
There
beginning.
is one
You
question.
talk about code.
Yeah, code be unfair.
Exactly. Is that or is it related with the FAIR for research software principles in some way?
In some way, they want to detail some points more suited to software.
Mm-hmm.
So, especially for the execution stage.
Okay.
So there are some different level: mandatory, recommended, optional.
Okay. I was not aware.
I don't know it will become a standard.
No, but
the initiative exists.
thanks.
Small question about the MOOC. Do you think it's useful for us to do it, or we will see all the stuff here?
I think there's some complementary part. The first one take 12 hours to do it, but the second one is there is some different software environment manager, for example, Geeks. There is some other tools, so it depends on your habits and what you want to learn.
There is also a part on workflows, computational workflows, which we won't cover here. So that could be interesting if you do a lot of data analysis.
It would be, but some heavy dataset management with Git also, some different aspects. So I think it's a complement.
Okay. No more questions? Thanks again, Céline.
Thank you again to you. Merci.